Yeah, thank you very, very much. Ladies and gentlemen, it's a real pleasure to be with you this afternoon. It's a wonderful venue and a great group. Just a word of introduction, supercharging. What is it? Engines develop power depending on the amount of air they can ingest. It's not a problem to provide the fuel. If you get the air in, you can always get enough fuel in to mix with the air to get the power. But air consumption is the determining factor in engine performance. And supercharging is a means of putting more air into the engine than atmospheric pressure will provide. Atmospheric pressure we rely on, generally speaking. Of course, more and more cars and trucks now are supercharged or turbocharged, but basically we've relied on atmospheric pressure for much of the history of the motor engine. Supercharging, you're using some kind of device, a blower, fan, pump, whatever you want to call it, to put more air into the engine than it would normally receive. And of course, there can be many reasons for doing that. It could be racing, get more power out of it. And our theme today concerns aviation. In the field of aviation, it's obvious that as an airplane rises, it gets into thinner and thinner air, and less air goes into the engine. This is a graph showing the rate at which that occurs. And it shows the reduction at 25,000 feet is only 30% able to develop 30% of the power that it could develop at sea level. It's just a rough indication, but that shows the degradation of power with increasing altitude. The earliest thoughts about supercharging aero engines concerned the opportunity to fly higher. It's very advantageous to fly as high as you can. You're out of the weather, for one thing, which is a boon. And also, the thinner air means easier passage through the air, less drag, more efficient performance at high altitude. Very, very beneficial. So when people in aviation first started to think about the possible benefits of supercharging, that was one of their objectives. Here in the UK, we have a very interesting pioneer. In October of 1909, George Mort in Willesden, a borough of London, was doing engineering for the New Engine Company. He lodged a patent on a two-stroke engine. I know you're familiar with the different two-stroke power pulse every revolution as opposed to the four-stroke where you have a pulse every other revolution. And it's a quite sophisticated two-stroke concept. One of its features is the use of a blower. And this is a blower akin to what we call a roots type blower with intersecting lobes. It looks a little bit like an oil pump or something like that, but you can see the blowers there at the side of this engine. And this is a concept that Mort brought into the metal in an aviation engine. His actual engines, starting around 1910, had 4-lobe rotors. So you saw in the patent days he had a 6-lobe rotor, but he used that. This is quite an efficient roots type blower with four rotors, in fact. The engine was very sophisticated in that Mort used the blower to bring air into the engine, initially to scavenge the gases from the previous stroke, and then he used a rotary valve to pump a rich mixture of air and fuel into the engine at the very last part of the induction stroke. This is going back up again. So the rotary valve played an important part in the way in which his engines operated. Another view of a cutaway NEC engine. Mort and the NEC produced engines of a number of different types in the years running up to the war. They had inline, we see an inline 6 here. He had 4s in V and inline versions, and these engines developed power from around 40 to around 100 horsepower. Very interesting early use of a blower. There was some supercharging effect from the way the ports and the rotary valve were organized, but not a lot. The objective of the blower here was not supercharging per se. It was for the performance of a two-stroke engine. But as you can see, a very sophisticated and interesting design. The engines did get some use, but the war intervened, and Mort's engines were too small, really, to be important in military terms. So he produced power units, parts for power units for other manufacturers during the war. Now, around 1915, as war got underway, it became evident to people on the front that against the German aircraft of the time, the Allied and British planes were viewed as Fokker fodder. The Fokkers were too tough. We couldn't get to grips with them. And one of the ways in which Britain's engineers thought to deal with this was to start thinking about a supercharger of some kind. And this work was done by the Royal Aircraft Factory. Britain at that time had a government company which designed and produced engines and aircraft for the military as a national activity. And to their credit, the engineers there looked into various different ways of providing a supercharger. They looked at piston-type compressors, the basic compressor that you know in industrial terms. That wasn't very satisfactory. They looked at roots-type blowers, and certainly the traditional two-lobe roots. They didn't like that because the pulses were too variable, caused their test engine to run erratically. They should have asked Mr. Mort, because he had a roots blower that was much more efficient and less likely to cause disturbance. Apparently they weren't aware of what he was doing. Vane-type blowers were also looked into. The type we know as the Wave or Shore type blower. But their conclusion was that a centrifugal supercharger would be the answer. Now, the centrifugal type supercharger has the advantage of being very efficient. It runs at extremely high speed relative to a typical aircraft engine running at 2,000 RPM. Your centrifugal blower will be running 16,000, 24,000 RPM. Because it gets its pumping ability from the inertia that it develops in the air that's going through it. And so it's very peaky in its performance, which is why it's not, historically, why it's not been very interesting for cars or even racing cars, because it doesn't give much boost at low speed, but in an aircraft engine, which is running at a fairly consistent speed, a centrifugal supercharger is quite good because you can match the blower to the engine and so forth. You're not going up and down the rev scale all the time. But this is basically the blower that the Royal Aircraft Factory designed for testing on their V8 engine. That was designed by Jimmy Eller. Jimmy Eller, E-L-L-O-R, is a kind of leitmotif through this whole story. In Britain, he became an outstanding designer, creator of superchargers, and this was Eller's, basically Eller's first effort. You can see the step-up gears that are needed to get the supercharger up to kind of speed that is necessary. In January 1916, this supercharger over here, oh sorry, this supercharger unit driven by a shaft from the back of the engine, and I should add, blowing through the carburetor into the engine. The British decided that that was the best way to do it. The French didn't. The French put the no, sorry, I got that backwards. At this stage, they were blowing through the carburetor. Later, they changed that and drew from the carburetor, which is, generally speaking, the best way to do it. This shows the test unit in January 1916, and as far as I can ascertain, this is the first compressor-aided aircraft engine to take flight. Nobody, French, German, Italians, beat the British to this honor. Sam Heron was another engineer involved in these developments, and he said the observer in the BE-2 biplane sat in the front seat with his feet under the fuel tank. The gear drive for the supercharger was also close to Elliot's feet, as you can see here, the observer. The gears were quite inadequate and the pinion failed in flight, producing showers of sparks and a feeling of distinct concern. They were discovering that the inertia, because of the high RPM of the centrifugal blower, was substantial, and that in fact the task of driving was no less demanding than driving the propeller of the airplane. So this is something that took a little while to sink in, that this was something that had to be paying attention to. The British, at this point, were pretty much committed to mechanical drive of the blower, centrifugal blower. In France, Auguste Rateau had been a terrific pioneer of turbine-driven centrifugal blowers for aircraft. In fact, he was really the first to build small turbine-powered units for aircraft use, using the exhaust of the engine to drive the supercharger. This, you can imagine, I mean, this was an unknown territory at the time. No one had made a turbine so small and doing such a very particular job under difficult circumstances. So Rateau's contribution was tremendous, no question. At this stage, Rateau had tried mechanical drive, but he now felt that turbine drive was, in spite of the difficulties, was the way to go with the supercharging. And just as an indication of how his system, this is a typical Rateau system, with the admission to the turbine from the exhaust, driving the turbine that in turn drove a centrifugal compressor, which drove the air through a radiator to cool it, an intercooling radiator, because of course compression raises air temperature. You don't want that going into the engine. Carburetor in this case, in the typical British installation. So this was all new science at the time of the First World War. Now, around this period, the British also decided that with sparks flying from the gears and so on, they should be investigating turbine-driven compressor. And Jimmy Eller was involved, along with Henry Fowler, designing Britain's own first turbocharger, which they were completing around 1917. And this is basically taken from their patent on the unit. It has an interesting feature in a little aneroid valve valve, sensing valve that adjusted the inlet of fuel to it was kind of a basic form of fuel injection into the annulus of the centrifugal fan. Now they had this practically ready when they found out that Rateau had some equipment available that they could use. And so they commenced testing with a Rateau system. And Rateau was pretty happy to let them do that. He said he'd like them to do it in France, and then they said, no, we prefer to do that at home, and so on. They did carry out testing with the Rateau system. But there were problems. There were failures of the pipework, failures of the blower. There was another reason. One observer said one of the problems is that the festoons of red-hot exhaust pipe from each cylinder to the turbine were considered too alarming to the pilot. It was. In those days, it was quite a lot of pipe work around. And the exhaust valves, of course, were suffering with the turbine back pressure and so forth, and the heat that was generated. So that represented a backpedaling by the British investigators. They decided that turbocharging at that time wasn't quite the way to go. We have another important pioneer. We all know the work of Harry Ricardo, who was a very important engineer in terms of new developments in technology, engines in particular. And Ricardo went to the War Office with ideas about how he could make engines that would perform better at high altitudes and so forth. And he said, the officer he went to see listened to me very courteously, and then said he was afraid I was wasting my time. The Army only required aircraft for artillery spotting, the officer informed him. And for this purpose, an altitude of only a few hundred feet was all that was needed. And in fact, captive balloons were the answer, he was told. So Ricardo got a very dusty response from the Army at that time. But he did complete a type of supercharging, which he himself admitted was not unlike something that Dugald-Clerk had developed in the 19th century. He in effect, added a stage below the main operating cylinder in which a pump effectively brought in with a certain level of timing through ports at the bottom of the cylinder and with a little bit of an intercooler here along the side that would integrate a form of supercharging with the engine itself. And in fact, he did manage the test engine. He had a test engine. He got a boost pressure of about 1/3 atmosphere, and significantly increased the engine's power from 21 to 31 horsepower. So it worked, which is not surprising. The stages to put it into actual use were difficult. He had a project to do a V12 engine. That didn't get done in any reasonable time. But at Beardmore, Frank Halford redesigned the company's engine to use the Ricardo supercharging. And this did succeed in increasing from 230 horsepower to 260 to power the engine. And they did. One of the disadvantages, of course, for an airplane is that the height of the engine is daunting to the pilot, very difficult for his vision. And they did produce ultimately an inverted version of this engine, which got over that problem. So, but this didn't get into practical use during the war, but it was, in its way, a fruitful avenue for exploration. Another player was John Davenport Siddeley. He was described as a man accustomed to having his own way and noted for being both energetic and somewhat autocratic. Siddeley Deasy Company was working on aircraft engines during the war. After the war, a series of amalgamations led to the creation of Armstrong Siddeley. In 1917, the Royal Aircraft Factory that I mentioned earlier was dissolved. This was not seen by the government as a really good way to be developing engines. Having a government body that was both designing them, producing them, they thought it better to rely on our aircraft engine producers, get them to do the work, and we can do research at Farnborough, where they were based. When that happened, Frederick Green, who had been leading the effort at Farnborough, and Sam Heron, whom I mentioned earlier, brought to Siddeley a 14-cylinder, two-row radial engine that they created at the RAF, Royal Aircraft Factory, which at that time, 1916-17, had a built-in centrifugal supercharger. So they hadn't really completed the engine, wasn't fully tested, but it came to Siddeley. And in 1919, the government, after the war, the government issued a contract for the further development of this engine, which became the Armstrong Siddeley Jaguar. And this was built and designed from start for integral supercharging built into the engine. And of course, you can get a sense here of the, how shall I say, the logic and the ease of marrying a radial engine with a supercharger, centrifugal supercharger. It was a natural. You've got the centrifugal blower at the back. You can take off the exit for air from various points, or one point, or wherever you'd like to do it in the correct way. The cylinders are all out there, and the boost is going outward centrifugally into the radial engine's cylinders. So it's quite a natural way for supercharging to be achieved, as opposed to an inline engine or V engine, where you've got quite a challenge with the pipe work involved. This engine, 22.4 liters, had first generated horsepower in 1916. And the post-war version that became the Jaguar began type testing in 1922, and soon they equipped it with a full supercharging kit, and that was the Jaguar 4 of 1925, which developed 365 horsepower. This was the first engine to be made commercially available with built-in supercharging by anybody. It was a very important pioneering effort by Armstrong Siddeley. Just a couple of details of the design. This shows the input drive to the blower from the engine. It's a kind of nest of the inner and outer gears and pinions, which were designed to accommodate any difference in angle or position of the elements of the supercharger in the engine. And this is the slipping clutches were coming into use because it was evident to designers, after much tearing of hair, that it was necessary to have some form of device that allowed slippage in the drive line up to a centrifugal blower. So this, you can see 4 different clutches, spring-loaded, but of course they're aided in their grip by centrifugal forces, and the planetary drive for the blower in this Jaguar engine had these clutches in all 3 of the of the epicyclic drive to the blower. So quite an intriguing piece of engineering. Again, Jimmy Eller was the author of that. And that's the resulting Jaguar engine. And again, that's the first production engine to have a supercharger from any country in the world. This was the Jaguar Major, which was rated at 400 horsepower at sea level and 500 horsepower at 14,000 feet. So this was terrific, very useful, and pioneering result for Armstrong's Siddeley. But somebody else was interested in these developments. This was Roy Fedden, another but quite different kind of hard driving executive engineer, chief engineer of Bristol Aeroplane Company, makers of both aircraft and engines, of course. And he wanted to see, he was interested to see what the problems were with the turbine-driven supercharger. The RAF had dropped it, but was it that bad, or what could be done? And in fact, the Royal Aircraft Establishment, as it was now named, did carry forward after the war some research into turbo-driven blowers. The first result of that was a marriage of a Bristol Jupiter 3 engine, which is a 28-liter, 29-liter, 9-cylinder engine, and it had attached to it at the back a turbocharging kit, again the work of Jimmy Eller, now at the Royal Aircraft Establishment. You can see here the blower is up at the top, and here it is, the exhaust coming out there, blowing down through an intercooler and then up through the carburetor array into the engine. Another view of that is viewed from the side. You can see how that was laid out. It was a very early adaptation, a little bit less elegant than you would hope would be the case. And again, quite a bit of exposed bits and bottoms. Now this was tested by the RAE. The installation was made by Bristol, and they made it in what was called a Bristol Sealy biplane. It was a unique airplane that Bristol had built for the competition. Didn't win the competition, but they had it available, so it became the test bed for this turbocharged engine. The Air Ministry bought this from Bristol in December of 1923 and proceeded to carry out tests with it. So this is, again, quite visible, the exhaust from the turbocharger in the Bristol Sealy. And one of the advantages of the Bristol Sealy was that it had an enclosed observer's position. So considering work at high altitude, this was seen as quite beneficial. And the turbocharging raised the service ceiling of this aircraft to 23,000 feet, and this was 6,000 feet higher than it could normally achieve as a service level of flight. So this was extremely promising. So the Air Ministry said, well, let's build a developed version of this. This was just a test bed. Let's go further and build a developed version. And the first one, this is kind of as far as I can tell, a kind of a test bed, a mule, based on the previous engine for this later version, but it's much more compact with the blower now mounted low down at the back. Here it is here, going through the intercooler and so forth. And this is the turbo unit itself that was developed jointly between Bristol and the Royal Aircraft Establishment. A look at the components of it. The turbine is at the left, of course, with a little cooling fan inside it, and the blades of the compressor toward the front. This in its final form, this was the Orion based on the Jupiter of 1928. This was tested in a Gloucester Gamecock fighter, and it gave excellent performance, extremely good climbing capability, 495 horsepower at altitude, 20,000 feet, and so forth. But there were problems. There were difficulties with the turbine wheel rubbing against the housing. There were, certain problems which really would be regarded as normal development problems. But the Air Ministry, based on these findings, stopped work on turbocharging for aircraft. And just a quote from a very good aviation historian, Bill Gunston: "In retrospect, it may have been a mistake to give up so easily. Fedden had too much on his plate, and in any case could not fund development himself. The national level, a fully developed turbocharger would have been a great advantage in the Second World War." This simply reflected the complete short-sightedness of the government in not appreciating the importance of such work. Fedden, in the meantime, in parallel with this, he's a very active guy, was developing a mechanically driven supercharger. He first did that for a smaller racing engine, and with the information he gathered from that, he applied inbuilt centrifugal blowing to the Jupiter, and the result was the Jupiter 7, which the military could have used and obtained from 1928. They first ran in April of 1927. Here's a look at the innards of the Jupiter 7. With, as I say, the blower very neatly nestling into the back of the engine, and in a good position to deliver an air-fuel mixture out in all directions to the various cylinders. So this was a very neat and attractive way to build an engine. Here we find Bristol racing away from Armstrong and Siddeley. Armstrong and Siddeley were first to have an engine that they were building in quantity for sale with a supercharger, with full supercharging. And the Bristol team, on the other hand, with the Jupiter 7 supercharged, built radials that were used around the world. Why did Armstrong Siddeley not capitalize on its advance and its advantage? And Sam Heron, one of the engineers involved in this period, said Bristol had an extremely aggressive development policy, whereas that of Armstrong and Siddeley was anything but aggressive. So Roy Fedden against John Siddeley, there was no contest. In fact, one of the French air salons around this period was described by one of the French publications as the scandale of Jupiter, because 70% of the airplanes on display, the European airplanes on display had Jupiter engines. So, bang. Fedden, Bristol, and Jupiter ran away with the prize. Just to look at a couple of the details of the Jupiter, you can see one of the clutches. Again, a clutch to allow some slippage in the drive when it occurs. An exploded view of the blower itself. You'll see quite a few aircraft engines of this period which look like they're supercharged, but in fact it was quite a popular thing to do to have a kind of rotating fan, if you will, at the back, not geared up very highly, as a kind of stirrer-upper of the mixture that made people feel distribution of the mixture among the various cylinders. But when properly geared up, it's quite another story. And a couple of cutaways of the supercharging unit on the Jupiter.
Can I ask you maybe
Sure.
pushed out to,
Yep, that's
I
good.
don't want to do it, but.
That's good, no, that's fine. Another view of that, that's, we'll look at the unit. Let's see, where am I? Okay. Okay. Three last slides. A very good customer for the Jupiter engine was Junkers. They bought the French license version made by known at Rome. It was a proper Jupiter, but made under license in France. And it was particularly suitable for this multi-purpose transport, the W-34, that Junkers built. Hugo Junkers was very interested to explore high altitudes, again, to try to verify this concept that flying high was more efficient and less fuel consumption, better speed, etc., with the help of supercharging. So he allocated one of his W-34s to high altitude research. He really wanted to see if flight above 12,000 meters really yielded important advantages in efficiency. This is one of the open cockpit aircraft. These are some of the people that he involved in this research. On the right is Reginald Schinzinger, who was the engineer assigned to the project. And it began trial flights in the autumn of 1928. So Junkers was doing this quite early in the history of the Jupiter. This was very much at the beginning of the Jupiter's activity. They found that they needed to lighten the plane. They also lengthened the wings from the standard configuration. And Willy Neuenhofen was the pilot. He's standing in the middle in this photograph. For Neuenhofen, a special oxygen delivery kit was developed, and that's what he's holding there. Neuenhofen is showing us the oxygen delivery kit. Just incidentally, he had a dead man's controller in the aircraft on the yoke. You had to squeeze the yoke all the time. If you let go of the yoke, the engine stopped. And this was because high altitude flight in those days was risky. You could conk out. And it did happen to him on one flight. He had trouble with the oxygen kit. He let go of the yoke. The airplane went down. He started, got going again. Anyway, on the 26th of May, 1929, Neuenhofen flew to 41,794 feet, setting a world altitude record. This was the first and the last time that a German aircraft and pilot set a official altitude record. And that was about half a mile higher than an American pilot had gone about 18 days earlier. And Neuenhofen held the record for more than a year. At that height, in an open cockpit airplane, flying behind a Jupiter, pretty good going, really. So now we're well on the way to using supercharging both for war and for peace. And I thank you for your attention.